Yes, today we'll start learning about controllers. In any feedback control system, a controller is introduced to modify the error signal and to achieve better control action. And the introduction of these controllers will modify the transient response and steady state error of the system. So on the whole, you get a better system. Now we have several sorts of controllers like proportional, proportional integral, proportional derivative, and proportional integral and derivative controllers. Now we'll learn about effect of proportional controller. The proportional controller produces an output signal which is proportional to error signal, and the transfer function is given by Kp, and this term is called gain of the controller. Proportional controller amplifies the error signal and increases the loop gain of the system, and the system behavior is improved by increasing loop gain, that is in terms of steady state tracking accuracy, and second one is disturbance signal rejection, and third one is relative stability. In addition to increase in loop gain, it decreases the sensitivity of the system to parameter variations, and the drawback in this proportional controller is that it produces a constant steady state error. Now we'll see the effect of PI controller. Proportional plus integral controller produces an output signal consisting of two terms. One is proportional to error signal, second one is proportional to integral of error signal. And the transfer function of PI controller is given by Kp into 1 plus 1 by Ti into S. You can rewrite this as Kp into Ti into S plus 1 by Tis, where Kp is proportional gain and Ti is equal to integral time. Now, this is the block diagram of unity feedback system with PI controller. This is a PI controller. Let the open loop transfer function G of S be a second order system with transfer function equal to omega n square by S into S plus 2 zeta omega n. Closed loop transfer function for this system is C of S by R of S equal to G of S by 1 plus G of S is equal to, for this system, Kp into 1 plus Ti into S by Ti into S into this, that is omega n square by S into S plus 2 zeta omega n by 1 plus Kp into 1 plus Ti into S by Ti into S into omega n square by S into S plus 2 zeta omega n. Now we'll simplify this. Kp into omega n square into 1 plus Ti into S. Taking the LCM here in the denominator, that is S square into Ti to S plus 2 zeta omega n plus Kp into omega n square into 1 plus Ti into S. Now from this, Kp into omega n square into 1 plus Ti into S by Ti multiplying S cube plus 2 zeta omega n into Ti S square plus Kp into omega n square plus Kp into omega n square Ti S. You can write this as Kp by Ti, taking out common, Ti n square plus 1 plus Ti into S, here S cube plus 2 zeta omega n into S square plus Kp into omega n square into S plus Kp by Ti into omega n square. Now we can write this as Ki into omega n square into 1 plus Ti into S by S cube plus 2 zeta omega n S square plus Kp into omega n square into S plus Ki into omega n square, where Ki is nothing but Kp by Ti. Now here in this closed loop transfer function, you can see that PI controller introduces a 0 in the system and increases the order by 1. Also, the type of the open loop system is also increased by 1. The increase in type number will result in reducing the steady state error. Now, the integral controller will reduce the error to 0. But the increase in the order of the system will result in a less stable system than the original, because higher order systems are less stable than lower order system. On the whole, proportional controller will give constant steady state error, where this integral controller will reduce the error to 0. If you do find this video useful, please like, share and subscribe.